Okay, class, today we'll look at ANSYS workbench case study. The problem is to perform a topology optimization for a structure here is with top fixed and at the end edge a 300 Newton force applied. As the constraint is maximum deformation for the structure is 0.3 millimeter. So the topology optimization achieved is to reduce the weight by 75%. Okay, so now let's go to ANSYS workbench, where we start from a static structural analysis. We'll perform a static structural analysis for the original design, and then based on that we'll do a topology optimization. Okay, so we create a static structure, and then we will go to geometry because the material we'll use is structural steel. So by it's a default material, we don't need to change the material property. Double click on geometry, where we'll create a geometry or draw the geometry. Okay, now we are in space claim. So select sketch, surface plane view, where we'll draw the sketch. So I move it a little bit downward and make sure that the units is a millimeter, because the geometry we have is a millimeter. Units, millimeter, looks good. Minor grid 1 millimeter, that's good. Okay, and then we will use line, start from center, draw 35 millimeter, and go up by 15 millimeter. Come back to left side 20, and then go up by 20 again. Okay, let's move down a little bit. 20, and then 15 left, go all the way downward to 35 to back to the origin. Alright, this is the 2D structure, and we'll pull up into 3D. So move around, click pull, change the perspective, and then pull by 2 millimeter. So the thickness is 2 millimeter. So after that, so with this, and we'll quit from, exit from space claim. Close it. Okay, and then we'll go to the model to perform force analysis, and then that will give our rough idea that how far away from the target. Our target is to constrain the deformation less than 0.3 millimeter, and the goal is to reduce the weight by 75%. Okay, now we have the geometry loaded. Check the material. Okay, go to structure steel, that's good, and then move on to mesh. Here, let's use 1 millimeter. So make sure that the unit you use is a millimeter. I'm using here is millimeter. So if you are using meter, you need to change it to a smaller number. Generate mesh. Right click, generate mesh. Okay, the mesh looks good. Then static structural, insert boundary condition, fix support on top surface. Surface filter has been set, apply. One more boundary condition, insert force, and this time the force will apply at the edge, which will use edge filter, apply. we'll use components to define the applied force. So if you look at the coordinate is along y direction downward, so we'll change y to minus 300 Newton. Okay, and then solution, we want to look at deformation, and we'll check the stress. Right click, solve. Okay, now we can look at the deformation. So if you look at the deformation with the original design, and the deformation is much smaller than 0.3. It's a 0.09, so we have a lot of space in terms of deformation to go. And equivalent stress, you will say that stress, the maximum stress shows up on the boundary. So that means if we cut the mass in the middle, and we highly possible we can still achieve the deformation constraint. Okay, and now with this information we'll close this, and the next step is to perform topology optimization. So in the analysis systems, drag this topology optimization all the way into the solution of the static structure. Again, topology optimization, drag to solution, and release. Now we have a topology optimization, and where we can click setup, because you can see there's a connection between solution to setup. That means we'll use the solution of static structure as the setup of topology optimization. Double click on setup, which will lead us to the topology optimization software. Now, still in a mechanical modeler, which is opened. And if you look at the topology optimization here, so this is based on static structure result. And in the topology optimization, we need to set up 3 things. The first thing is the optimization region. So by default, the optimization region is the whole area except the region which we set a fixed boundary gradation, except the top. So see the desired region topology, this is the region that will perform topology optimization. The object, second item is the object. Objective is this objective. The objective is that we can set as a compliance mass or volume. Here we'll use compliance, and to achieve minimum compliance. If we achieve minimum compliance, that means when the compliance is small, that means the deformation is small. So that means we minimize deformation. Okay, so equivalent to minimum deformation. That's the second item. The third item is response constraints. The response constraints, where we can change is go to the details. Here you can response, we can change to different items. Here we'll use mass. And remember that we want to reduce the mass by 75%. That means the percent to retain, that will be 25%. So we set as 25%, and then we can start our solution. So go to solution, solve. Okay, now we have the result, so which is topology density. So if you look at the topology, and some of the materials has been reduced in the middle. So, and this is a preliminary result. And you will notice that if you look at the boundary, if you look at the when it cut off the materials, the surface is quite rough. So the next step is we want to repair the geometry, make it smooth, and validate the result. Okay, so then we'll go to the next step to smooth the surface as well as to validate the result. So we can close this result. And we'll generate a new one by right click on the result. So you select result, right click, and select transfer to design validation system. Which will generate a new static structural project. Again, this step is right click on result and to validate the system. Okay, now we have a new static structure where we can validate, and we will first to repair the geometry, make it smooth, and then validate the result. So before doing that, we need to update the result here. Right click on result, update. Okay, now the update finished. The next step is to update the geometry. So the result of B will become the geometry of C. And then once we import the geometry from B to C, and in the geometry we'll make repair to smooth the surface. Okay, the next step is we'll double click. See, if you look at the check mark, that means it's accomplished. And then double click on geometry, where we'll repair the geometry to smooth the surface. Okay, now we are in space claim again. This time you'll see that we have two geometries. One is the original design, the second one is after topology optimization. Well, we can check off this original design. Click this check. Here now we have the optimized surface, which has the rough surface. So what we'll do is to repair it. So to repair it, we'll keep it this optimization here, and we'll copy a new one so we can make modification. Okay, again, we will keep this here, we'll copy this, and we'll make a revision based on the copied one. To do that, what you can do is use sketch mode and click on the surface, and then let me zoom in a little bit and use a plan view, and then we'll select, now we're on the surface, we select this surface, could drag a rectangle to select the whole surface, and then go to the left corner, see there is a copy, click a copy, Okay, and then click paste. Now we have two. We have paste the surface of the optimized surface, and then we check off the original optimization one, and then we have this surface copied from the optimized rough surface. Okay, so and actually you can tell that this is a rough surface here. Okay, so we'll do some repairment based on the copied curves. The first thing we can do is make a overall quick repair is to go to repair tab and click on fit curve. Okay, and make some smooth. And you can tell from that, from the dot, you can tell that from which part it has been fit into a straight line. Okay, so after that, click the complete. Now we have this surface, but still that if you move your cursor around, you'll see that some of them are straight lines, but from this point to this point we want one straight line, but there's multiples. And again, we still need some repair. For detailed repair, what we can do is we can use a trim away function. For example, here we can trim away this lines, and then we use a line to connect from one end to the other end. Okay. We can do the same thing, trim away these lines, and we do connection again. Okay, so trim away this line, the thing we don't really want, to have. So we want to use one straight line to connect them. So what we can do is connect them, and then connect them. One more. See, this looks good. This is okay. Okay, that looks good. Okay, so now next step is we will repair the corners. So again, we'll use a trim away to trim away all these corners. So trim away those corners. We'll trim away all these corners, and then we'll use the round corner function to generate a corner for it, where you can use a value that you want to set up. So here I will use 2 to be consistent. Whenever I is able to use 2, I will use 2. Okay, now we have this finished. Well, I noticed there's a small piece left here. Let's trim that away. Okay, now we have this surface. So when you do the repair, and then this is not unique. Okay, so this repair is not unique, and the general principle is to use a round in the corner, and also use a straight line between. Okay. Also, you may notice that there's something not very straight. So for this line, there are 2 straight lines, which is not great. So we can make a prepare again. We can round it up again. Okay. Now that looks good. So well, now we have this, the surface will pull into a 3D. So click pull and let's delete surface in between. Now we'll change set the thickness. Okay, before setting the thickness, what I want to do is I will click on this surface and I will use this ruler. Okay, click on the ruler. The reason I do that before pull into 3D is we want set the thickness as a parameter, which will become optimization parameter input in the future for next project. Okay, so so here you just follow my instruction. So what I do is, again, I will Control Z. I will do it again. Before pulling into a 3D, what you do is to click on the surface, okay, and set the ruler, okay, and then click on the surface again, and then pull it up by 2 millimeters. So if you set the ruler, what you will see that there is a P shows up there. So after setup, it shows that P. That means that will become a parameter which can do optimization later. Okay, so click on P, and then a new group has been created. If you go to the group, you'll see that there's a new group which is the thickness of this ruler, and then we can rename it thickness, which will become a parameter for future optimization. Okay, right, now we have this one, and we can close it. Oh, before we close it, don't close it yet. Before we close it, I want to suppress for physics for this one, for make sure that both of them are suppressed. So we're only left with the one that we have a smoother surface. Okay, so which will perform a stress analysis again. Now you can exit and then go to the model. So you'll see that we have set a parameter for further optimization, and there's a panel showed up bottom that there's a parameter set. Double click on model, click yes, and where we can do the stress analysis again. Still loading, so we need to wait. Okay, now here we need to assign a material to it, structural steel. So again, if you forget to suppress the other part, the other solid part, in space claim here you can suppress it still work. Okay, so we have suppressed the other part, so only one left, which is a smoothed structure, and then we generate mesh again, and here see that the fixed support force is still there, but we need let as a model know that which part we want apply. So we want to apply fixed support on top. We want to apply force. See the magnitude minus 300 newtons still there. We need to the modeler which part, this edge, then apply, and then we can solve it. And this step is to validate the result. Okay, it's finished. You can check the deformation. The deformation is 0.2 millimeter, which is smaller than 0.3. That means we still have some space, can go further, optimize it. Okay, and this is stress. And well, but for this one we'll stop here. But before moving, before exist. So what we'll do is we'll set 2 more parameters for next project, which we'll do in next lecture. Okay, so we'll set 2 more parameters for optimization. Why is this deformation? The deformation here, if you look at the maximum deformation 0.2 millimeter, we have some space to go. You can click it, and then it become maximum. And so you set P here, then so we will have 1 more parameter, and then we need another parameter, which is you go click on geometry. In the details of geometry, go to property, which is this mass. The mass will become another parameter for optimization. So remember that we want to reduce 75%, and we'll do a detailed optimization in the on the next level. Okay, so now we set 2 more parameters in this step, and plus the parameter we have set in previous space claim, where we set a thickness. So we have 3 parameters in total. So with these 3 parameters, we can do a design experiment optimization, which will be the topic or project for next lecture. Okay, now you can close this part, and here you can see that we have set up the parameters for next step. You double click on it, you see that we have P1 thickness, we have static structure, we have P2, P3, which one is deformation maximum, the other one is geometry. Well, this video is already very long, so we'll stop here, and for next video we'll follow this and to continue work on it.